Far from being just destroyers, black holes are the invisible engines powering the grand design of the cosmos. Black holes, those invisible giants that swallow everything in their path, are often portrayed as cosmic monsters. But what if we have misunderstood them all along? What if, instead of tearing the universe apart, they are actually shaping it, building galaxies, influencing the flow of matter, and orchestrating the grand design of the cosmos? In the vast, silent theater of space, black holes are the unseen directors. From the centers of galaxies to the edge of known physics, they are the gravitational anchors that hold our universe together and possibly even define its very structure. These enigmatic objects, born from the collapse of massive stars or formed in the earliest moments after the Big Bang, are not just endpoints, they are engines, they are architects. In this video, we will dive into the fascinating truth about black holes, not as cosmic anomalies, but as fundamental forces sculpting the universe we live in. From shaping galaxies to influencing time, matter, and the fate of stars, black holes are at the heart of cosmic evolution. Let's begin by exploring the foundational role they play in our universe. How they act not as destroyers, but as the architects of the universe. When we hear the word black hole, we often imagine an all-consuming monster in space, something that devours stars, planets, and even light. While this image isn't entirely wrong, it only tells one part of the story. In reality, black holes play a far more constructive and foundational role in shaping the structure of the universe. They don't just destroy, they organize, influence, and help create the very cosmic architecture we see today. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape from it. At the center of a black hole lies a point called singularity, where density becomes infinite and the known laws of physics break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. But black holes aren't just random cosmic glitches. They come in different sizes and types. The most important ones, from the structural standpoint, are the supermassive black holes, millions to billions of times the mass of our Sun, found at the center of most galaxies, including our own Milky Way. Every large galaxy we observe seems to have a supermassive black hole at its core. For example, the Milky Way contains a center black hole known as Sagittarius A star, which has a mass of about 4 million suns. But this isn't a coincidence. These black holes appear to play a crucial role in holding their host galaxies together. Their immense gravity helps stabilize the orbit of stars and interstellar gas around the galactic center. Without them, many galaxies might never have formed into the organized spiral and elliptical shapes we observe today. In this sense, black holes act like gravitational anchors. They shape the galaxy structure, influence how stars move, and may even control the growth of the galaxy over billions of years. One of the biggest puzzles in modern astrophysics is understanding how these massive black holes formed so early in the universe's history. We observed supermassive black holes existing less than a billion years after the Big Bang. This raises the question, how did they grow so large so quickly? There are few theories. One suggests that direct collapse of massive gas clouds in the early universe could have formed black holes without needing to go through the typical life cycle of a star. Others propose that smaller black holes may have merged repeatedly to form giants. Whichever path they took, it's clear that black holes appeared early, and their presence has been shaping the universe ever since. It may seem strange, but black holes can control when and how stars are born. How? Through something called feedback. As matter spirals into a black hole, it heats up and emits huge amount of energy, especially in the form of X-rays and powerful jet particles. This energy can blow away clouds of gas that would otherwise collapse to form new stars. In this way, black holes can suppress star formation by ejecting or heating the raw materials needed to make stars. But at the same time, under certain conditions, these jets can also compress gas clouds, triggering star formation. This dual role makes black holes both creators and regulators of the stellar population in galaxies. Another astonishing fact is the observed correlation between the mass of a galaxy's central black hole and the mass of its galactic bulge. The more massive the black hole, the more massive the galaxy's bulge tends to be. This relationship suggests a deep connection between black hole growth and galaxy formation. Somehow, the two processes are intertwined, even though the black hole is tiny compared to the size of the entire galaxy. This remains an active area of research, but it reinforces the idea that black holes are fundamental to the cosmic architecture, not just isolated oddities. When black holes consume matter, they release enormous amounts of energy. This energy can heat intergalactic gas, power quasars, and even shape galaxy clusters. These processes are essential in the formation of large-scale structures across the universe. In the early universe, quasars powered by black holes acted as beacons visible across billions of light years. Their influence extended far beyond their host galaxies, affecting the temperature and composition of vast cosmic regions. Without these cosmic engines, the universe might look very different today, colder, quieter, and less structured. On an even larger scale, black holes influence galaxy clusters. Group of hundreds or even thousands of galaxies held together by gravity. In the centers of these clusters, supermassive black holes is the largest galaxies often pump out energy into the surrounding gas. Without this energy, the gas would cool and condense rapidly, forming too many stars too quickly. By heating the gas, the black holes prevent runaway star formation, ensuring that galaxy clusters evolve in a more stable way over cosmic timescales. Zooming out even further, we find that galaxies aren't randomly scattered. They form a cosmic web made up of filaments and voids. Gravity is the primary force shaping this large-scale structure, and black holes, through their mass, radiation, and influence, play a central part in guiding the growth of these cosmic filaments. Massive black holes anchor galaxies, and galaxies align along gravitational highways, creating the web-like appearance of the universe. Without black holes, the gravitational dynamics of these structures would be fundamentally altered. We saw how black holes act as architects of the universe, organizing galaxies, regulating star formation, and anchoring cosmic structures. But black holes are more than just gravitational anchors. They are extreme objects where the fundamental fabric of reality, space, and time is stretched, twisted, and sometimes completely broken. Now, we explore the true power of black holes, not just in terms of mass or gravity, but in how they fundamentally shape reality itself. Gravity is the weakest of the four fundamental forces in nature. But black holes reveal that what happens when gravity is pushed to its absolute limit. A black hole's gravitational pull is so strong that beyond a certain boundary, the event horizon, nothing, not even light, can escape. This boundary acts as one-way door. Once crossed, escape becomes impossible. No signal, no information, no object can return from inside. The strength of gravity near a black hole distorts not only space but also time. According to Einstein's general theory of relativity, massive objects curve space-time. Black holes, with their immense density, curve it so sharply that time itself behaves differently. One of the most mind-bending consequences of a black hole's power is time dilation. The closer you get to a black hole, the slower time moves relative to an outside observer. This is not science fiction. This is confirmed by Einstein's equations and even demonstrated on a smaller scale by GPS satellites orbiting Earth, which experience time slightly faster than clocks on the surface due to lower gravity. But near a black hole, the effect becomes dramatic. For someone hovering just outside the event horizon, time for them might seem normal, but to a distant observer, they appear to be frozen in time. This phenomenon inspired the famous scene in Interstellar, where an hour near a black hole equates to years outside. This kind of time warping isn't just an idea, it's a real effect with measurable consequences. Black holes gives us a direct window into how gravity manipulates time. Another extreme effect caused by the intense gravity of black holes is what physicists call spaghettification, a result of tidal forces. Tidal forces occur because the force of gravity changes with distance. Near a black hole, the difference in gravity between your feet and your head can become so great that you would be stretched vertically and compressed horizontally, like spaghetti. This happens most dramatically with stellar mass black holes, where the tidal gradient near the event horizon is much stronger than in supermassive black holes. In theory, you could cross the event horizon of a supermassive black hole without immediately experiencing spaghettification. But in smaller black holes, it happens much earlier. This gruesome fate is not just a thought experiment. We have observed stars being torn apart by black holes, an event known as tidal disruption event, where a star gets too close and is shredded by gravity. Despite being invisible, black holes can be surrounded by some of the brightest objects in the universe. When matter falls towards a black hole, it doesn't usually fall in directly. It forms a swirling accretion disk, a disk of gas, dust, and debris heated to millions of degrees as it spirals inward. These superheated materials emit intense radiation, often in X-rays, and can outshine an entire galaxy. In fact, many quasars, the most luminous objects ever observed, are powered by supermassive black holes feeding at the center of young galaxies. Some quasars are over 1 trillion times brighter than our Sun. Yet, all of that energy comes from material falling into a single invisible point. Accretion disks are not just sources of light, they are laboratories of extreme physics, showing us how energy is extracted from matter under the most intense conditions. In many active black holes, especially in quasars and radio galaxies, we observe enormous relativistic jets, narrow beams of particles traveling near the speed of light, often extending thousands of light years into space. These jets are launched not from inside the black hole but from just outside the event horizon, where magnetic fields and rotating matter create conditions powerful enough to eject material at relativistic speeds. Relativistic jets can influence entire galaxies by injecting energy far from the black hole itself, affecting star formation and intergalactic environments. What's remarkable is that an object which swallows everything can also project massive amounts of matter and energy across the cosmos, showing that black holes are not just gravitational vacuums, they are dynamic engines of transformation. One of the most profound mysteries surrounding black holes is the information paradox. In quantum physics, information about a system state is never truly lost. But when something falls into a black hole and the black hole eventually evaporates, where does that information go? If it's destroyed, it violates quantum mechanics. If it escapes, how does it do so? This paradox has puzzled physicists for decades and represents a key problem in the intersection of general relativity and quantum mechanics. Black holes are forcing scientists to rethink our understanding of space, time, entropy, and the very nature of reality. Some proposals include holographic principle, suggesting the universe behave like a 3D projection of 2D information stored on a surface. Firewall theories propose violent energetic boundaries inside black holes, and even the idea that information is encoded in Hawking radiation. So far, there is no consensus that black holes are proving to be the ultimate testing ground for unifying the laws of universe. Some speculative theories suggest that the inside of a black hole beyond the event horizon might not be the end, but rather a gateway. Certain solutions to Einstein's equation suggest the existence of wormhole and white holes, theoretical opposite of black holes that expel matter instead of pulling in it. In theory, black holes could be connected to other regions of space-time or even other universes. While we have no observational evidence for this and such ideas remain speculative, it shows how black holes push the boundaries of what we consider physically possible. We saw how black holes manipulate the fabric of reality, warping time, igniting extreme radiation, and even challenging the foundation of physics. But now, let's zoom out from the event horizon and look at the bigger picture. How do black holes influence the overall structure and evolution of the universe? What we will uncover is that black holes are not isolated monsters tearing through space, they are cosmic sculptors, silently shaping the destiny of galaxies, clusters, and possibly the very web of the cosmos itself. The large-scale structure of the universe forms what's called the cosmic web, a vast network of galaxies, galaxy clusters, and dark matter filaments stretching across billions of light years. This structure is not random, it follows the gravitational evolution of the early universe after the Big Bang. At the intersection of these cosmic filaments, we often find massive galaxy clusters. And at the heart of most large galaxies, within those clusters, lies a supermassive black hole. While gravity from dark matter and normal matter help build the web, it is now believed that black holes help shape the fine structure within, influencing how galaxy clusters evolve and distribute their stars and gas. Supermassive black holes, through their activity, regulate the growth of galaxies within the web, preventing them from growing too quickly or collapsing into chaotic mergers. Thus, they help preserve the intricate geometry of the cosmic web over billions of years. At first glance, black holes and star formation might seem unrelated, but their connection is profound. When a supermassive black hole at the center of galaxy feeds on surrounding material, it enters an active galactic nucleus phase. During this time, the energy released from the accretion disk and relativistic jets can heat the gas in the galaxy and even push it out of the galaxy altogether. This process is known as AGN feedback, and it's critical because it prevents runaway star formation. If a galaxy formed stars too rapidly, it would consume all its gas in a short time, leaving no material for future generation of stars or planetary systems. AGN feedback provides a regulating mechanism, a kind of cosmic thermostat, that ensures steady, sustainable star formation over billions of years. This has been confirmed by observations of elliptical galaxies with massive black holes that are no longer forming new stars. These galaxies were likely shut down by powerful AGN activity in the past. There is a fascinating and well-documented relationship between the mass of a supermassive black hole and the mass of its host galaxy's central bulge. This correlation, known as the M-sigma relation, suggests a deep co-evolutionary link between a galaxy and its central black hole. Even though a black hole might weigh only 0.1% or less of the galaxy's mass, it somehow tracks the evolution of the entire system. This implies that the black hole isn't just passively sitting in the middle, instead it grows the tandem with the galaxy. As the galaxy forms stars and builds structures, the black holes consume gas and regulates the entire system's behavior. No current theory of galaxy formation is complete without accounting for this black hole-galaxy connection. In this way, black holes sculpt the mass, shape, and composition of their host galaxies. When two galaxies collide, a common event in cosmic history, their central black holes eventually sink toward the center of the merged galaxy and form a supermassive black hole binary. As these black holes spiral toward each other, they release enormous amounts of energy in the formation of gravitational waves. Ripples in space-time, first predicted by Einstein and directly detected by LIGO in 2015. Eventually, the black holes merge, forming an even larger supermassive black hole. These mergers can restructure entire galaxies, triggering bursts of star formation and reshaping the galaxy's morphology, from spiral to elliptical, for instance. Thus, through gravitational interaction and energetic feedback, black holes are key players in determining what kinds of galaxies exist in our universe. Black holes also shape our universe through the bending of light. Because their gravitational field is so intense, black holes cause a dramatic curvature in space-time. Light passing near them is bent, a phenomena known as gravitational lensing. While massive galaxies and dark matter halos are the more common gravitational lenses, isolated black holes can also bend the light of background stars. If a black hole passes in front of a star, from our point of view, the star appears to be brighten and then dim in a predictable pattern. This technique called microlensing helps us locate and measure black holes that don't emit light, especially the elusive intermediate mass black holes. So, even in silence, black holes leave their observable effects that let us map their presence and understand their distribution in the universe. One of the lesser known roles black holes might play is in the distribution of dark matter. Dark matter is invisible, but its gravitational influence shapes the formation of galaxies. Recent simulations suggest that the growth of central black holes could actually alter the density profile of dark matter halos surrounding galaxies. The idea is that black holes accrete matters and blow out gas. They stir the dark matter in the inner regions, changing how it clusters. This could explain why some galaxies have flatter dark matter cores than predicted. Though this area is still under investigation, it hints at a potential link between black holes and the invisible scaffolding of the universe. On the larger scale, black holes may have even influenced the ultimate destiny of the cosmos. In a universe dominated by dark energy, galaxies are drifting further apart. But inside galaxies, black holes are steadily consuming matter, stars, and gas. Over unimaginable timescales, trillions of years, black holes may be the last surviving structures. As stars die out and galaxies dim, black holes could persist, slowly evaporating via Hawking radiation, shrinking over time until they vanish. This far future epoch, called the black hole era, would mark a universe where these invisible giants, once cosmic sculptors, become the final whispers of structures in an otherwise dark and empty cosmos. Black holes sculpt galaxies, regulate star formation, and even interact with dark matter. But how do these effects play out across billions of years? Now, we will dive deeper into the role of black holes in galactic evolution, how they influence the life cycle of galaxies, from youthful spirals to ancient ellipticals, and why every galaxy's past and future is tied to the black hole at its heart. In our journey so far, we have uncovered how black holes are not just destructive beasts, they are master regulators, cosmic architects, and silent influencers of galactic behavior. But perhaps their most remarkable role lies in how they secretly govern the evolution of galaxies themselves. Galaxies are the building blocks of the universe, and at the core of nearly every large galaxy is a supermassive black hole, millions to billions of times the mass of the Sun. These invisible giants don't just sit idle, they are intimately tied to a galaxy's past, present, and future. Now we will uncover how black holes act as a hidden engines, driving the formation, transformation, and death of galaxies across cosmic time. Let's begin with a fundamental truth of modern astrophysics. Almost every large galaxy has a supermassive black hole at its center. This was not always known. For decades, black holes were thought to be rare, but observations with powerful telescopes like Hubble and Chandra revealed that active galactic nuclei powered by accreting black holes are common in the distant universe. Even in seemingly quiet galaxies like our own Milky Way, the presence of a central black hole is now undeniable. The Milky Way's Sagittarius A star with a mass of around 4 million suns is a perfect example. The fact that galaxy mass and black hole mass are correlated implies an co-evolutionary process. In other words, as galaxies grow, so do their black holes and vice versa. Black holes grow by accreting gas and matter. When galaxies collide or when gas flows inward toward the galactic center, massive amounts of material fall into the black hole's grasp. During this phase, the black hole can become an AGN, lighting up the galaxy's core across the electromagnetic spectrum: visible light, X-rays, gamma rays, even radio waves. This is not a quiet process. As matter falls inward, it heats up and forms a blazing accretion disk, releasing vast energy, sometimes outshining the entire galaxy. The most extreme versions of this process are called quasars. Supermassive black holes devouring matters at the rate of up to 1,000 solar masses per year. Quasars were more common in the early universe, around 10 billion years ago, and represent key phases in black hole and galaxy growth. So, when galaxies evolve, their black holes don't passively watch, they feed, radiate, transform their host environments. A critical way black holes drive galactic evolution is through feedback, the energy and momentum they inject into the galaxy. There are two primary forms of AGN feedback: radiative feedback and kinetic feedback. Radiative feedback involves intense light and winds from the accretion disk pushing gas away from the galaxy center. Whereas kinetic feedback involves powerful jets of relativistic particles that can stretch hundreds of thousands of light years beyond the galaxy. These feedback mechanisms have major consequences. They heat up the interstellar gas, preventing it from cooling and collapsing into stars. They can blow gas completely out of the galaxy, reducing future star formation. They help stabilize galactic growth, avoiding unchecked starburst. Without this regulation, galaxies might grow too fast and burn out early. Instead, AGN feedback ensures slower, more sustained evolutionary path. Galaxies come in many shapes: spiral, elliptical, irregular, and these shapes evolve over time. One of the most dramatic evolutionary transitions is from spiral to elliptical galaxies, and black holes play a central role. When two spiral galaxies merge, the gravitational chaos funnels gas towards the center, igniting starburst and triggering rapid black hole growth. Eventually, the central black holes merge, releasing powerful feedback that heats or ejects remaining gas. With no gas left to form stars, the galaxy settles into an elliptical shape, older, redder, and more passive. This transformation is driven in part by the black hole's ability to quench star formation, altering not just the galaxy's star population but its entire morphology. Hence, black holes help sculpt galactic identities, deciding whether a galaxy remains spiral, becomes elliptical, or enters a dormant phase. Black holes are thought to be a primary quenching mechanism, especially in massive galaxies. Here is how. As the black hole grows and it enters a high-energy AGN phase, it heats or removes cold molecular gases. This gas is the fuel for star formation. Without it, the galaxy becomes red and dead. Observations show that the most massive quenched galaxies tend to have larger central black holes. While other processes like environmental effects can also quench star formation, black hole feedback is considered the most efficient internal driver, especially in central isolated galaxies. So, In a very real sense, a galaxy's death as a star formation system is often written by its central black hole. Here is a fascinating cosmic twist. The most massive black holes formed early in the universe's history, while smaller black holes are still growing today. This phenomena is known as cosmic downsizing. It suggests that larger galaxies and their black holes evolved quickly, whereas smaller systems took longer. Why does this matter? Because it reveals that black hole activity shaped galaxy evolution early on, influencing how galaxies matured across cosmic time. The quasar era, roughly 10 billion years ago, was the peak of black hole growth and feedback. After that, most galaxies and their black holes entered a quiet phase. Smaller galaxies continued evolving with more subtle black hole influence. This tells us that black holes didn't just evolve with galaxies, they set the timeline of evolution for different types of galaxies. While supermassive black holes dominate large galaxies, researchers are also exploring how intermediate black holes formed. These black holes are harder to detect, but evidence is mounting that they regulate small-scale environments much like their larger cousins. In dwarf galaxies, black holes may still provide feedback, regulate star formation, and shape the distribution of dark matter. Understanding these systems could reveal how black holes formed in the early universe before growing into their modern supermassive forms. So, whether we are looking at giant elliptical galaxies or tiny dwarf systems, black holes play a hidden but vital role in shaping their evolution. We have seen how black holes shapes galaxies, regulate star formation, and influence cosmic evolution. Yet, for all their external effects, one region remains fundamentally hidden: the interior of a black hole. The so-called event horizon is not just a boundary in space, it's a one-way gate to a region where our current laws of physics break down. Now, we go where even light cannot escape, into the very mystery at the heart of black holes. What happens beyond the event horizon? What does a singularity really mean? And could black holes be more than just gravitational traps? Perhaps even gateways to new realms of physics. The event horizon is the defining feature of a black hole. It's the boundary beyond which nothing can return, not even light. Once anything, matter, energy, or even information crosses this boundary, it is said to be casually disconnected from the rest of the universe. From the outside, the event horizon marks the point of no return. For a non-rotating black hole, it's a perfect sphere. For rotating black holes, it's flattened at the poles due to frame dragging. But here is the strange part. Crossing the event horizon doesn't feel like hitting a wall. According to general relativity, someone falling in wouldn't notice any physical boundary. Yet, for outside observers, that person would appear to freeze in time at the horizon, forever fading into darkness. This apparent contradiction sets the stage for one of the greatest puzzles in modern physics. At the very core of a black hole lies the singularity, a point where matter is compressed to infinite density and space-time curvature becomes infinite. Here is the problem. While general relativity predicts the singularity, it cannot describe what actually happens there. The equations literally break down at the singularity, meaning they stop making physical sense. That's why physicists believe that a new theory is needed, something that unites general relativity and quantum mechanics. Until such a theory exists, often called quantum gravity, we cannot truly say we understand what happens inside a black hole. The singularity represents a frontier of knowledge and possibly the key to new physics. In the 1970s, Stephen Hawking made a groundbreaking discovery. Black holes aren't completely black. Thanks to quantum effects near the event horizon, they should emit tiny amounts of radiation now called Hawking radiation. Over time, this radiation causes the black hole to lose mass and eventually evaporate completely. Here is where the real mystery deepens. If a black hole can vanish, what happens to all the information about the matter it once consumed? Quantum mechanics tells us that information can't be destroyed. Yet, if Hawking radiation is truly random, it carries no information about what fell in. This leads to the black hole information paradox, a direct clash between quantum physics and general relativity. Some proposed solutions include information escapes subtly in the radiation, or the information is stored on the event horizon, or black holes don't actually destroy information, they just scramble it. This paradox remains one of the biggest unsolved problems in physics. One radical attempt to resolve the information paradox is the firewall hypothesis. Proposed in 2012, it suggests that an infalling observer wouldn't experience a smooth crossing at the event horizon. Instead, they would encounter a wall of high energy particles, a firewall that destroys all information. This idea breaks the principle of no drama in general relativity. The notion that nothing special happens at the horizon, but it might preserve unitarity in quantum mechanics. The firewall idea is controversial. It implies that either quantum mechanics or general relativity must be wrong or incomplete in black hole context. No one knows for sure, but the debate has forced physicists to rethink their core assumptions. Could black holes be more than just cosmic dead ends? Some solutions to Einstein equations like the Einstein-Rosen bridge allows for wormholes, theoretical tunnels connecting two distant points in space-time. A wormhole could, in theory, allow travel between galaxies or even between universes. But to remain stable, it would require exotic matter with negative energy density which has never been observed. Another possibility is the white hole, the time reverse of a black hole. Instead of pulling everything in, it spits everything out, but cannot be entered. White holes are purely theoretical and no observational evidence supports their existence, but they appear as valid solutions in general relativity. Some theories propose that black holes transition into white holes at the end of their life cycle, releasing all the stored information in one burst, potentially resolving the information paradox. While speculative, these ideas are valuable because they push the boundaries of theoretical physics. To truly understand what lies beyond the event horizon, we need a quantum theory of gravity, a unified framework that describes both the fabric of space-time and the quantum rules of particles and energy. Two leading candidates are string theory and loop quantum gravity. These theories are still under development, but they aim to replace the singularity with a new state of matter or geometry that obeys both quantum and gravitational rules. Until we can experimentally test them, these remain theoretical frontiers, but they are the best tools we have for understanding the interior of black holes. Directly observing a black hole's interior is impossible. By definition, no light escapes. But indirect clues may help us understand what's happening inside. Gravitational waves detected by black hole mergers, those ripples in space-time may carry subtle information about event horizon and internal structures. Accretion behavior, studying how matter moves near the horizon, gives clues about black holes' geometry. Event Horizon Telescope, the famous image of M87's black hole, gave us our first direct view of black hole's shadow. Future upgrades might reveal more about the space just outside the event horizon. While we can't see past the horizon, the universe might still have fingerprints of black holes' interiors in observational phenomena. From the invisible heart of galaxies to the most distant reaches of the observable universe, black holes are far more than cosmic anomalies. They are not just the aftermath of stellar death or the final chapters of collapsed giants. They are, in many ways, the cosmic regulators, the unseen engines driving galactic formation, evolution, and even the distribution of matter across the universe. We have uncovered how black holes form in stellar cores and the centers of galaxies, how it shapes entire galaxies through feedback jets and winds, how it influences cosmic structure through gravity and energy, and how it preserves the memory of galactic collision and ancient cosmic events. What once seemed like cosmic destroyers have now emerged as cosmic architects. Their gravitational pull not only consumes but also creates. Their energy output not only destroys but also regulates and reshapes. Their presence not only marks the end of matter but also the beginning of structure. And yet, for all we have learned, black hole remains shrouded in mystery. What lies beyond the event horizon? Are black holes connected to wormholes or alternate universe? Can they hold the key to a quantum theory of gravity? Could they even be the seeds of new universes in a multiverse? The quest to understand black holes is not just about physics, it's a journey into the deepest questions of existence, of time, space, origin, and destiny. In a universe that expands, cools, and evolves, black holes may be the guardians of memory, keeping a gravitational record of how the cosmos came to be. So, the next time you look up at the night sky, remember, behind the starlight, beyond the nebulae, and within the very galaxies themselves lie the dark engines of the universe, black holes, silently shaping the story of everything.